All right, let's go ahead and get started. Any questions before we jump back into things? All right, so we finished 8-6 last time. Uh, Basically, been talking about power series for the last week or so. Um, so basically, what we've done in the last couple sections was basically given a function, if we can somehow represent that function as something like a geometric series or the sum of a geometric series, then we can manipulate it and turn it into a power series. So now what we're going to do is something called Taylor Taylor series expansion or Maclaurin series expansion, which basically allows us to take any function and turn it into a power series. So let's kind of build up on what we've talked about. So if I have a power series, all power series look like this. So basically ascending powers of x, all those terms are multiplied by some coefficient. If I have a power series representation of a function, then basically what I'm saying is this, or let's back up a little bit. What values of x does that series have to converge for? Or does it have to converge at all? So we talked about three situations for how a series might converge. It either might converge for every value of x, so from negative infinity to infinity, or it could converge for like some finitely long interval. That's what you call the radius of convergence. Or like the most restrictive cases where it converges only at one place. So in this case, that'd be x equals 0. So if x equals 0, what does this series up there look like? Well, what do all the terms in that sum look like? They're all just 0, right? That converges, but in kind of a trivial, meaningless way. Um, so one thing we haven't mentioned here is that what does it mean for a converge? For convergence, basically, that means the function, so whatever function I have, f, and the power series have to completely agree. So let's talk about what that means to completely agree. So let's say I have some function f, and I can represent it as a power series that looks like this. C naught plus C1x plus C2x squared. Six terms how to do it. So basically what I'm saying is assume I have some function where, at the very least, I don't know about anywhere else, but where x equals 0, the function, the power series have to agree, right? What does that mean, though? What does that mean for them to agree? So one thing it should mean is that, so if I graph a couple of things here, let's say my function looks like this. Mm. Let's say I just take the first term of this power series. If I have a function that looks like, so if I have the first term, that first term is just a constant, right? If I were to graph that, it would look like this. So does that, and I haven't really defined what this means, what this complete agreement means, but if they share one point in common, that has to be part of it, right? If I say that two functions completely agree at one point, they should at least have that point in common, right? So let's kind of build this up. I know that f of 0 should be equal to c naught. But can we still say that those two functions are the same? Just because they share that point in common. What else should they have in common? All the values. So, I mean, let's build that up. So, yeah, they have that point in common, but it would also be helpful if they had, you know, maybe the same slope. So let's take the derivative of this thing we just made. So we know that f of 0 has to equal c0. If I take a derivative of this thing, what does that look like? 0. What's the first not 0 term? c1 2c2x plus 3c3 x squared plus 4c4 x to the third plus 5c5 x to the fourth, right? So what is f prime of 0? So if I want to take the derivative of this function at 1, or sorry, at 0, what would be left with? Or in other words, what is f prime of 0? C1. But really, if I want complete agreement between these two functions, I want all their derivatives to be the same, right? So all orders. So how are f and f prime related to each other? Derivative, right? So if I'm saying that the function f is equal to this power series, then the derivative has to be equal to the derivative of that power series. So basically, it's when I plug in 0, what remains? C1. So let's do at least a couple more orders of this. If I take the second derivative, what do I have? 2c2 plus 6c3 plus 12c4. Wait, I left off next, didn't I? Plus 12c4x squared plus 20c5x cubed. So what's f double prime of 0? 2c2. Let's do one more and see if we can build out a pattern here. What's the next derivative? 6c3 plus 24c4x plus 60 c to the fifth, or c5x squared, right? So what's f triple prime? 6c3. So let's start cataloging these things to the right here. And I'm going to solve for what these constants are, or what these coefficients. So c naught is equal to f of 0. c1 is equal to f prime of 0. c2 is equal to f double, or no. c2 is equal to f double prime of 0 over 2. c3 is equal to f triple prime of 0 over 6. Can I say what C4 is? Do we see a pattern emerging at all? So F, the fourth derivative of F at 0 over 24. Can we generalize that at all? Can we see that, how to do that? So I mean, what's happened to what am I doing with the function? I'm basically taking higher and higher order derivatives, right? So the thing we have to worry about is getting a handle on that denominator. Can I generalize this? What is C of Cn? So it'll be the nth derivative of the function at 0. But what does that denominator look like? So 1, then 2, then 6, then 24. Any idea what the next one would be? Right?
Is it the N exclamation point?
Yeah, it's the n factorial. So that's basically what's going on here is as we keep taking derivatives, think about what happens to these derivatives. Basically, can I follow a term here? Yeah, let's follow this one here. That became 3C3, and then you multiply it by 2, multiply it by 1. That's 3 factorial. Or with the next one up, 4 times 3 times 2. And we can go any further, but 4 times 3 times 2 times 1. So basically all those denominators are going to be a factorial depending on basically what order derivative is this. So why the heck do we do this? So now that we kind of have this template, basically we can take any function, as long as that function has derivatives, we can build up a power series for it like this, and we can get all of those coefficients basically by taking a bunch of derivatives at the point where we care about. So that's the rationale. So again, what's the purpose of this? Basically, I want to take any function, and not really any function, but any differentiable. So basically, nothing that we just did works for a function that doesn't have derivatives. So basically, any differentiable function, no matter what it looks like, and basically turn it into a polynomial. So those polynomials look like this. So we kind of built out these terms. So first term has nothing to do with derivatives, just evaluating the function at whatever point I care about. Then the first derivative, second derivative, and so on. So talk a lot about what these things look like. So yeah, let's pause here, kind of make sure we understand like what the structure of it is. Ask me whatever questions you have. So in general, this thing is called a Taylor series, named after Brooke Taylor, the person who first published it. But you'll also see this term Maclaurin series. A Maclaurin series is a Taylor series. It's just when you see that name, we're assuming that the center value is 0. Basically, every power series, every series has to converge for a single value of x. Basically, that's in a Maclaurin series, that center value, that single value of x is 0. It might converge more places, but that's the one that's always guaranteed. Questions here? Go ahead.
Is A just a constant?
A is basically that's the value of x for where this thing converges. So basically, if I back up, this thing here, the way I wrote this power series assumed that that single value where we converge is x equals 0. In general, that's a little too restrictive. So we can think about a power series like this. N goes from 0 to infinity. I still have some list of coefficients that we call C sub n. And instead of writing x to the power of n, I'll write x minus a to the power of n. So basically that a is like the center of this, the center of where this thing converges. So it might have a radius of convergence where it converges for like maybe 4 units above A and 4 units below A and everything between. Or it could be infinite, but no matter what, it has to converge at that one place. Because let's say this, if x equals, so if I build out this power series, if x equals A, what do all the terms in this series look like? 0. So you get this convergence in a very meaningless way. But it is guaranteed to converge there because basically you're just adding a bunch of zeros. How are we doing? I believe and I hope that if we do a couple of concrete examples, this will sink in a bit. So let's do that. So e to the x, f of x equals e to the x. This is very much not a geometric sum. I cannot do anything to make this look like a geometric sum. But because of what we're doing with, because now with this new tool of Taylor series, we can still come up with a power series for this. So basically what I'm trying to build up is, I'm going to call this function t for Taylor. And what do those things look like? They look like the sum of all these terms from n to infinity. And I'm saying the center value is a equals 0. What is it that tells me that? The name Maclaurin means that that's the center, a equals 0. So basically, this is what power series look like. The thing we're going to figure out now is basically how to get these C sub n terms. So let's write a first few of them out and see if we can get any kind of patterns from them. What does C naught equal to? So in general, C naught is equal to whatever the function is equal to at its center value. So let's write these in general, and then we'll put some specificity behind them. So C1 comes from f prime of 0. C2 comes from f prime of 0 over 2 factorial. C3 comes from f double prime. Oh, no. Lying to you. C2 comes from f double prime of 0. C3 comes f triple prime of 0 over 6 factorial. So everything I've written down so far has nothing to do with e to the x. These are all just generally the way you build out these power series. Go ahead.
You're saying we only go to C3.
Because I have to stop. There's just, hopefully we're going to get a pattern out of this.
Oh.
In fact, I suspect that we'll see a pattern earlier. If I'm wrong, we got to run 5 terms, we'll do it. I just,
Okay, I'm sure there's.
yeah, I just have to stop somewhere. In reality, these Taylor series they have an infinite number of terms, which is why this is the goal, is to generalize them, because otherwise there's no way to accurately portray it.
But besides that one, is there logic how to go to 6 factorial?
Yeah, I lied to you. It's not 6 factorial, it's 3 factorial, which ends up becoming 6. Got ahead of myself. No, in general, it's over. Yeah, so c to the n is equal to the nth derivative evaluated at whatever the center value is over n factorial. So again, none of this has anything to do with the function that we actually care about. So now let's figure out the things we care about. For us, what is f of 0? It's e to the 0, which is 1. Over here, I'll say the function and we'll write down some derivatives. What's f prime of x? E to the x. Okay, so that's e to the 0 again, right? So 1. What's f double prime of x? E to the x. Are we seeing why we starting with this one? Go away, HP. So this is going to be a little different. E to the 0 over 2, which is a half. Are we satisfied that all these are going to be 1 over something? So this will be 1 over 6. So my first 4 coefficients are 1, 1, 1/2, and 1/6. Can I generalize them at all? Right, so the derivative is always going to be, so the derivative of this function is always going to be e to the x. And I'm always going to be evaluating that function at 0. So I'm always going to get 1, right? Questions on that so far? So now we write out our first few terms. I think this is going to be 1 plus x plus 1/2 x squared plus 1/6 x cubed. We didn't go any further, but can you tell me the next couple of terms? Just so we can make sure we have a handle on what's happening. What would the next term be? 1/24 x to the fourth and something x to the fifth, probably. What's the coefficient? 1/120. So 24 times 5. So this is the first six terms. But again, I can't just keep writing out terms, so let's try to compact this. Can I define this sigma notation? X to the n over n factorial. Is that really going to fit? So here's the thing. You told me just a minute ago that C sub n in general is going to be 1/n factorial, right? We still agree with this? We okay with where that came from? If you believe that, then getting the power series. So what's the difference between this thing and this thing here? How did I get from the coefficients of the power series to the full power series? So one thing to note is that all Maclaurin series are going to look like this. This series of some list of coefficients times x to the power of n. So once I have a handle on what the coefficients are doing, then I can basically incorporate the x terms. So the x to the power of n. So I think this right here is that's my Taylor series for e to the x. So e to the x, very much not a polynomial, but that Taylor series, it's not technically a polynomial because it has infinitely many terms, but I can represent e to the x as that function. Go ahead.
And then once we get the power series, would we then just do like the normal operations to get the radius conversion?
Yeah, let's do it now. So one thing I want to point out is we had a huge shortcut to find the radii of convergence for the series we talked about last time. So basically we just looked at common ratio, right? Can we do that here? Now, there is no geometric kind of crutch to fall back on here. So because of that, if I want the radius convergence, we're looking at the ratio test. So it's probably been a little bit since we've talked about that, at least all together. How does that ratio test work? Of what? Yep, so some term divided by the term before it in general. So what does that look like for us? Okay, so you're already breaking it down. N plus 1 times n factorial. Okay. Is there anything, what can I simplify or cancel out here? So what's left with the x's? X over n plus 1, right? What is that limit? That comes out to 0, right? So that limit comes out to exactly 0. The x gets overwhelmed. Because of that, what do we know about the convergence of this table? So yeah, it converges for every single value of x. So this is a very good Taylor series because it's valid for all values of x. So this is kind of the ideal situation. We took a function that is not a polynomial, and we showed that not only can it be represented as a polynomial, but it can be represented by that polynomial absolutely everywhere. So any questions on how we did that? All right. Shall we?
Is there a more efficient way to do it other than taking the derivative at each value?
So I mean, I'm willing to bet that for at least some of us, probably could have stopped manually dealing with derivatives somewhere early on. I think this is going to sound like a cop out, but I think it's all I can offer you. I think the efficiency is going to come from us just getting comfortable with it. But really, the idea of taking, hopefully, you don't have to take more than a few derivatives to kind of understand what the trends are. All right, so now let's change a couple of things. So what changes have I made here? Change the center. So that's a equals 2. Change the function slightly. So how should we start? So let's start looking at what our coefficients are. So what is C0 going to come from? F of 0, I slightly disagree. F of 2. So, and that's a thing that it's very common to work around x equals 0, but sometimes you have to recalibrate. So our first term is going to come from f of 2, which is what? E to the negative 2. How about the next term? F prime of 2, which is what? Negative e to the negative 2. So let's put a reminder out here. If f of x equals e to the negative x, what is f prime of x? Negative e to the negative x. What is f double prime of x? E to the negative x. What is the 21st derivative of x? How do you know? It's odd. So basically, it alternates back and forth. There's only 2 different derivatives that come out of this. So maybe that tells you something about what the Taylor series is going to look like. So because we understand how those derivatives are going to behave, do I know what C2 is going to look like? E to the negative 2 over 2. Okay, so I got the first 3 coefficients. It sounds like we're getting a sense of some of the patterns that are cropping up. So what can we do now? So yeah, let's write down what C sub n is. So basically, this is probably going to be where most of your work is done, where the most crucial things are decided. Can we generalize this C sub n? Negative 1 to the power of n. So we've got an alternation, so we've got to have an alternating term. What else? E to the negative 2 over n factorial. So let's make sure we know we need alternation, but let's make sure that it alternates. Let's make sure the thing we wrote down alternates in the way we think it should. We think it's okay, or we think that needs to be adjusted. If you start at n equals 0, you get a positive term, which is what you. So I think that as written is fine. So good, we have C sub n. What can we do with that? Okay, so now in general, what a Taylor series look like, or what a power series look like? This series, this sum of all the C sub n's times x minus a to the power of n. So now we have that C sub n. I can rewrite this. F of x equals this sum, -1 to the n times e to the -2 over n factorial times x minus 2 to the power of n. How are we doing with that?
So that left side, essentially,
Yeah, it's not essentially, it's exactly what that is. Yeah, the C sub n, basically what a big part of what we have to build here is a formula for C sub n. It's one thing to find a few of these, but then working that into, a generalization of the whole list, and that's a big part of this. All right. Any questions on how we got the definition of the series itself? Can we find out where it converges? Ratio test should give us that. So any suspicions about where this converges yet? So we would hope that since e to the x converges for all real numbers, that e to the negative x should do something similar. So I'm not doing this right. So there's the a. I'm totally leaving off the x minus 2 part. Why? All right. What cancels? And factorial cancels. Right. E to the -2 is a constant. And I think the absolute value really takes the alternation out of this. So a lot of this goes away. So this equals what? The limit of x minus 2 over n plus 1. Absolute value of x minus 2 over n plus 1. What happens with that limit? That goes to 0 again, which is always less than 1. So we have convergence everywhere. How are we doing? Go ahead. Yeah, that's a good question. That's kind of a big. Yeah, so why? No. Why did I get rid of the -1 terms entirely? So it's not because they cancel out, it's because the absolute value will make them into 1. What else? Okay. All right, we've done a couple of these, so I'll take my cues from you. How would you like to start? First three coefficients. All right, what's the first coefficient? F of 0. How do you know it's 0? Maclaurin series is by default gives you, yeah, I want this to be centered at 0. What is the sign of 0? 0. Cosine of 0, which is 1. C2 is equal to? Yeah, I'll write 0 over 2, just to be clear we're paying attention to that. What's the next derivative? So I'm going to be missing. I'm going to have a lot of 0 terms, right? So that's something we have to kind of pay attention to. I think it's worthwhile to get at least 2 more. Well, 2 more non-zero ones. Is it okay if I assume that C4 is 0? What is the fifth derivative of sine of x? How do you know? Right. So basically it's a 4 cycle. So cosine 0 over what? 5 factorial or 120. So 1 over 120. I'm going to skip ahead to C7. I think we can safely assume that every even one will vanish. What is C7? Negative cosine 0 over 7 factorial, which is not a number I know off the top of my head. I'm happy to just leave it. So here's the thing. I think this is going to make it a little trickier to deal with C sub n. Because a lot of we have to, basically we're going to be missing a lot of terms. So one thing I encourage here is let's actually write out the first several terms of the Taylor series. So this is going to be, what's the first non-zero term of my series going to be? Not 1. The coefficient is going to be 1, but what's the full term? C1x. So maybe for now I'll include the 0. So 0 plus x plus 0 minus 1/6 what? X cubed. Plus 0 plus what? X to the 5th over 120 plus 0 minus x to the 7th over whatever 7 factorial is. All right. So I think we have the first 8 terms. Now what? Yeah, so let's clear the deck and actually look at the things let's just look at the things we need to worry about. So x minus x cubed over 6 plus x to the 5th over 120 minus x to the 7th over 7 factorial. All right, so can we generalize here? Negative 1 to the n minus 1. Why n minus 1 and not just n? The first term needs to be positive.
Oh.
Oh, yeah, I think. Now I mean, it's good to make sure. So that -1 to the n is going to give us the alternation in the correct way. X squared to the n. Y squared, not just x. Right, so basically the powers on x are counted up by 2 each term. So let's look at the x squared to the n term. Is that really what we want? What's the first term going to be? The first term is going to have an x power of 0, right? The second term is going to have an x power of 2, and then 4, and then 6. So
Times x.
what's that?
Times x.
If we multiply that by an x, we'll get back to where we want, right? Let's make sure. Now, when n equals 0, what's my first power of x going to be? X. And then the second one's going to be, or when n equals 1, what's the power of x going to be? 2, 3. And then 5. And I think that works, right? Go ahead.
You're speaking to the conclusion that you didn't want to provide the x.
Yeah. Caleb, that was you. Where'd your other x come from?
Because the first term is just x, and we're starting at n equals 0. So if we have x squared to n, it'll just be 1. So we need an x to start out with.
Right. So based on that, I'm going to say exactly what he said in different words. Basically, the thing that we originally built here, all of our powers on x are going to be exactly 1 too low everywhere. So multiplying it by a single power of x is a good repair. All right, I think we're mostly doing well now. What? Over something factorial. So now we got to figure out what goes in that factorial. Maybe it'd be helpful if we rewrote these 4 terms here as actual factorials. 120 is what factorial? 5, 6s, and can I call this x over 1 factorial? Does that help? Let's make a table. Is it not just n? I don't think it is, because basically, let's say this. For n, basically, here's what I want. I want to map values of n to whatever lives inside this question mark before I take a factorial of it, right? So n equals 0, n equals 1, n equals 2, n equals 3. So my first term has a what inside the factorial? A 1, right? And then this, when n equals 1, it's over 3 factorial. And then 5. And then 7. What's the relationship between n and this? Basically, I'm trying to like, I shouldn't call it x. We're already using x. So what am I doing to n to figure out the thing that winds up in the factorial? Times 2 and then add 1 to it, right? Is that going to fit everywhere? Seems good. So yeah, I think if you just make it n, then you're going to have 0 basically, then you'd have x over 0 factorial, which fits. But then you'd have negative minus x to the third over 1 factorial, which doesn't work. So we need to do a little bit of basically needed to come up with a linear function that gave us the denominators we actually want. Is that thing good now? I will suggest this to kind of clean it up a little bit. I'm going to say x to the power of 2n plus 1. Is it clear that that's identical to what we wrote down? Or what's written down above it? Questions so far? Go ahead.
Would you mind explaining?
Yeah, absolutely. So the values in the table come directly from this list of things right here. Because basically the reason for that table, we're trying to figure out, all right, for any given value of n, what does my denominator look like? So when n equals 0, basically here's the thing, even though I've like lost a lot of terms, I still want my series to be built on n equals 0, n equals 1, n equals 2, and so on.
So instead of going with the 0 plus x, we're starting just from the non-zero values of 1, 0. Okay.
Right. Because it's basically, I'm saying it's very hard, and it actually might be impossible to try to have the 0 terms pop up in here. It's easier just to ignore them and kind of work around. But yeah, I think that's the main thrust here, is that even though we are very used to, if n equals 7, that means the power on x is 7. I'm encouraging us to kind of get away from that, is that let's just stick with the non-zero terms. Anything else about this? I mean,
figuring out that.
I don't want to say in general yes, but here they absolutely mirror each other, right? So if you do see that they follow the same trend, then yeah, you can absolutely mimic that 2n plus 1 here. All right, anything else? We have a couple minutes left. Can we see where this converges? How do we do that? Ratio test? Any suspicions on where this converges? -1 to 1? All right, let's see. Ratio test, so -1 to the n plus 1 times x to the 2n plus 3. We understand why it's 2n plus 3 and not 2n plus 2. So in case you're wondering, basically, it's not enough to just add 1 to whatever's going on around n. We have to substitute n plus 1 in for n. And everywhere I see an n, that's being multiplied by 2, right? So really, these things are going to increase by 2 instead of 1. So times 2n plus 1 factorial over -1 to the n times x to the 2n plus 1. All right, so does anything convenient happen for us here? My factorials cancel out. This x term cancels out. So let's rewrite a new thing. The limit as n goes to infinity of the alternation I'm going to ignore. So x squared over 2n plus 3 times 2n plus 2. Can we evaluate that limit? It goes 0. So where does this series converge? Everywhere. So yeah, Taylor series for sine of x is ideal. It converges absolutely everywhere. It's identical, or it's equivalent to sine of x. The factorial for, oh, yeah. I can. I'm going to go to the chalkboard, though. I'm going to keep the integrity of this thing and not try to buy space back.